So I guess I'm going to talk about decisions and economics, and those are two topics I know very little about. So maybe together I'll know something about them. This is a fairly standard view of economics. We have a collection of agents or people that are selfish, not in the sense that they're necessarily egotistic, but in the sense that each agent follows their own agenda. And they create and allocate and exchange various limited resources. And it's a standard assumption in economics that when you view such a system, it is normally in some state of equilibrium that I'm not going to specify precisely here at the moment. But at least most of the time, this is the way it seems to people who observe it. Now, the system is an enormous distributed system in the sense that the control of the system is given to these agents. They have local knowledge, so knowledge is also distributed in this system. They don't, unlike our classical distributed systems in computer science, they're not engineered to follow any common goal, so the system is not engineered. In the spirit of this morning's talk, we are taking here a scientific view and not a engineering view of what we're doing. The question that, or the focus of this talk is about, is the following natural questions. How is such a system driven to seem to be in a state of equilibrium when there is no overall control or no engineering that actually forces it to be in a state of equilibrium? So that's one question that we could ask about such a system. What kind, so this is not a question of how to make decisions. It's a question of what are plausible decisions of the agents that lead the system to a state of equilibrium. And of course, since economic systems are not really stable, they change over time, and sometimes there's some drastic changes. A natural question or a natural follow-up question is how is equilibrium restored when the system is driven out of equilibrium? So these are obviously questions about the dynamics or the stability of the system. And our goal is to search for plausible reasons why equilibrium exists in these systems. So I'm going to talk a little bit about various approaches to this question. So in game theory, dynamics usually mean that we have some underlying game, that's the stage game, and the agents simply play this game repeatedly, so they play the same game again and again. And but they know they're going to play it again and again, so they can design their actions in view of the fact that they're going to play this game indefinitely. And this is how game theory views dynamics. The game theoretic view simply produces a longer game. This repeated game is just a longer game that has more available strategies. And then game theory designed all sorts of solution concepts that are supposed to capture the behavior of agents under the incentives that the game produces for them. normally in these situations, what game theorists look at are these extensive form equilibria. There are various sorts of them. I'm not going to go into their details. Things like subgame perfect equilibria and or sequential equilibria and various other notions of equilibrium. Very generally speaking, the idea there is that the agents actually compute in advance all the optimal moves for all possible situations of the system and all possible visible actions of the other agents, and then they play basically their best strategy taking into account all the possibilities of the game. So in effect, these equilibria notions are actually a static notion because you unravel the entire evolution of the game in advance and play optimally against that, taking into account, of course, what the other players will do. And this poses several problems to our goal. So first technical problem is that these solutions are often intractable. So in fact, it's not clear how agents would actually come about to play them because they can't compute them efficiently as far as we know. It also requires players to be unrealistically prescient. So they actually need to know or they need to think about what will happen in this game forever. And it's actually surprising that most economists view the economy as behaving this way. So the current state of the economy actually is assumed to take into account all possible eventualities of what will happen in the future and to incorporate all that in the current equilibrium. And of course, if you're unrealistically prescient, it's very hard for you to adapt to unexpected changes of the economy. So in this respect, this is unrealistic because players normally would take into account the fact that the economy will at some point change in ways that they can't currently predict. So what would we want to have from a more realistic dynamic view of an economic system? Well, it would be nice to have all sorts of things. So here's a list of them. We want the decisions or the moves of the agents to have some empirical evidence that this is actually what people do under these circumstances. We want to have some justification for these moves. So we want some form of rationality or of rational decision making by the agents. They're not completely. The model should have some justification for these moves. Now, this might be a bit more debatable, but this is something that seems reasonable, is that the agents themselves, there's no particular reason for them to aim for equilibrium. They are trying to achieve their own goals, their own agenda. So often in what I will describe, moves are or certain dynamics that were suggested actually very carefully damp the moves in order to achieve equilibrium. And that doesn't seem to be like a good model that explains how equilibrium comes about, because it basically makes decisions directed towards achieving equilibrium rather than being motivated by what? Yes?
Are you ruling out discounted costs, discounted payoffs as a damping? Is that part of damping?
I'm not talking about any specific model right now, but just in very general. So yes, I might even rule out discounted payoffs in the repeated game for that reason. But I'll talk about it a bit more precisely in the next slide, what I actually mean here. In general, I mean here that it doesn't seem a decision process that aims at equilibrium doesn't seem to be a reasonable explanation of how equilibrium comes about. I mean, it's a good engineering practice, perhaps, but it's not a good explanation. And of course, we want to see that, these decision processes that we model lead to some attractive outcome or some form of equilibrium. They converge to that, and they converge to that quickly. And the reason we hope to see quick convergence is exactly this last point, that we should expect, because when we view the economy, it's normally in equilibrium, we expect it to, and the economy itself, of course, the conditions change all the time. This quick convergence is almost a requirement for the economy to follow equilibrium over a long period of time, or to follow it usually or normally over a long period of time. So as soon as conditions change, we expect the economy to move to the new equilibrium rather quickly. Otherwise, we will see long periods of time where the economy is out of equilibrium. Okay, so there's a whole, other than these extensive form equilibria, there's a whole different notion of dynamics in game theory and in economics in general that fall under this rubric of learning dynamics. There are various forms of them. I'll only mention, there are some of them mentioned here, and I'll go over even fewer of the ones mentioned here. So one rather attractive kind of dynamics are these no-regret dynamics. We know them in computer science as essentially multiplicative weights, even though they could be more general than that. They're known to converge in any game, in any stage game, to something called a correlated equilibrium. Doesn't really matter what it means right now. So they suffer from this problem that, first of all, it's not known how to implement them for all games. But in cases where they are implemented, the reactions of the agents have to be rather carefully adjusted so that they achieve this no-regret guarantee. And this seems to lack any strategic justification. So it's not clear even that if you know that everybody is playing a no-regret dynamic, that this is what you should follow. Maybe you should do something else. They provide some guarantee, but it's not clear why agents should do this thing. There's sort of a very myopic version of learning dynamics that does seem to have some sort of justification in certain cases. This is best response. So best response simply means that if I'm in some situation, I optimize my next step. And this is the exact opposite of these extensive form equilibria. So I'm just looking at the next step. I'm not looking any distance into the future, and I'm optimizing that. So this is one form of bounded rationality. I have very limited foresight. I just try to optimize my next step. The problem with this, of course, is that it's not clear that it leads to any desirable outcome. In fact, in many cases, it doesn't. But in some cases it does. So it's known to lead to some form of equilibrium in some cases, but not in all cases. There are all sorts of other forms that I won't go into. This is a damped version of best response, for instance. The thing that will interest us mostly in this talk is this level K model, which is almost the same as receding horizon control in control theory. So the idea here is the following. We have a limited look ahead. So we look ahead only k steps of the game, or at most k steps of the game, and then we basically optimize that, and that will be our response. So this kind of behavior has some empirical evidence. So there have been a lot of experiments on people playing games, and this is the kind of strategy that they tend to choose. We know, for instance, that when you, this is something just folklore knowledge, that when you play chess, you try to, you can't compute all the steps ahead, but you try to compute a few steps ahead and maybe prune some of them. And this seems to be a way that people play games in general. And it also has some relation to various forms of learning of games that I won't go into. So it's something that has some, at least initial justification to look into. So we're going to study these things in a rather restricted setting. We're going to study them in Fisher markets, and these are Fisher markets. This is the model. We have m perfectly divisible goods. That means you can buy any quantity of them, any fractional quantity of them. And we will assume that each of these goods is owned by a single seller. So that is one side of the market. Each good has one seller that is selling it. Because they're perfectly divisible, we can scale the quantity in the market to be 1 for all the goods. And the demand is generated by n buyers. We won't really be concerned about the individuality of the buyers. So the gain that we will look into is the seller side. So they're n buyers. Each buyer has a budget and has some concave utility function. And so they're looking to buy their best basket of goods based on the utility function, but subject to the budget constraint that they have. Now here is more precisely how demand is generated. Every good J has some price, varying price Pj, and the game that we will look into is how these prices are set. Every buyer has a budget, so buyer I has a budget Bi. And it has a utility function Ui of Xi, where Xi is simply a basket of goods that this buyer buys. So for every possible combination of goods, the buyer has a utility function Ui, and Ui is assumed to be concave here. Xij is the quantity of good J that buyer I is buying. Now, the demand that I generates is the basket that generates the maximum utility subject to the constraint that the cost of this basket is bounded by the budget. And of course, the demand for good J at prices P is simply the aggregate demand for all the buyers for that good. Now, at equilibrium, this is the standard notion of market equilibrium. So equilibrium is achieved by a price vector P star for which the demand, the aggregate demand for each of the goods is exactly 1, is exactly the supply. So the equilibrium notion that we're using here is that the market clears, supply equals demand. And in the setting that we will consider, P star is going to be unique, but this is not necessarily generally the case. We also need the notion of elasticity of demand. So elasticity of demand simply measures the percentage of change in demand as a function of the percentage of change in the price. And you can talk about the own elasticity, so how the demand for J is affected by its own price, and you can talk about cross elasticities, which is how the demand for J is affected by the prices of other goods. And we're going to assume the following assumptions. I'll call this elastic and bounded demand. We're assuming that all the cross price elasticities are at least 0. This means that the demand is weak growth substitutes, which means that raising the price for good K cannot decrease the demand for good J. And the own price elasticities are less than -1. This implies or is equivalent to saying that each seller has an incentive to clear the market no matter what the other prices are. Clear the market for the good that they're holding. Otherwise, if this doesn't hold, then sellers have an incentive to raise the price and have the demand be less than the supply. And we're also going to assume some that prices are bounded. So if all the prices are very low, all the demands are going to be bigger than 1, and if all the prices are very big, then all the demands are going to be less than 1. So these are the assumptions that we're going to make. Now about price updates. We're going to think of a repeated game of sorts, where in each round new prices are announced, and then the sellers observe the demand that these new prices create. And you can think of this in various settings. So in the synchronous setting, all prices are modified simultaneously in synchronous rounds, and we observe everything simultaneously. In an asynchronous setting, maybe some of the price, so each price is updated at its own rate, which means that at any given point in time, we may observe only some updates, but not all of them. And then there is this more elaborate and I think most promising model, but I'm not going to talk about it here, of ongoing markets that Colin Fleischer introduced, where I think this actually might explain equilibrium in the best way. In this model, not only the price updates are asynchronous, but also the market signals are arbitrarily but boundedly delayed. So you don't actually act upon fresh information, but the information could be in one side or in both sides. So both price information and demand information may be somewhat delayed, and I think this actually is the most promising direction in explaining. Yes?
Is it delayed differently for different buyers and sellers?
Yeah, so it's delayed differently for different, yes. But there is some, let's say, some bound on the amount of delay, and it's arbitrary. It's not a fixed delay. So I think actually these delays might be important in explaining how dynamically a market reaches equilibrium, rather than this instantaneous view of. So there's a classical process that seems to explain equilibrium. Specifically in this setting, it's known to explain equilibrium, and that's proportional to atonement. So the original process by Walras, which was not very concrete, and the more concrete version of Samuelson were both in continuous time, so they were essentially talking about differential equations, but we will discuss discrete timed atonement, and this is how discrete timed atonement looks like. So basically what you do is what you would naturally do. If there is excess demand, you would raise your price, and if there's excess supply, you would lower your price. And specifically, discrete time proportional to atonement, or one version of it, looks like this. There's some empirical evidence from experiments that, in fact, this is how people update prices in markets. These are small-scale experiments, so it's not clear that they reflect what actually happens in a real market, but there is some rather extensive evidence that this is what might happen. And what's interesting is that this seems to happen even in cases where atonement does not converge to an equilibrium. There are such cases, not the type of markets I'm talking about here, but there are cases where this might happen. It's known to converge in various settings, but again, we have this problem that the process does not seem natural in the sense that it requires careful damping for it to work and to converge to equilibrium. And this is just a picture that about these CS utilities versus our restrictions. So there is an overlapping region, but they're not identical, and none includes the other. Okay, so we discussed best response. So what is best response here? Best response simply means the following thing. Each seller J acts as follows. It assumes that all the other prices are going to stay put in the next iteration, and then it updates its own price to optimize its revenue given the assumption that the other prices are not going to change. And under our own price elasticity assumption, this simply means that we assume here that the sellers know everything about the market. They know all the utility functions. So they can actually calculate this. So this simply means that buyer J is going to choose a price that clears its own good. Yes?
So it's not clear to me why they want to clear the good. Isn't it possible that if they don't sell everything, they actually might get a better revenue?
That's exactly why we're making this. This assumption implies that.
Yeah, but maybe that assumption isn't true. I guess.
Yeah, if that assumption isn't true, then this is not true either. Then they want to raise their price as much as possible. Yeah. I mean, this is exactly what this assumption means.
Yeah.
Now, of course, it's not always true.
What is the general theorem about the existence of market clearing prices for Fisher markets? Does it assume this kind of elasticity?
They always exist. Market clearing prices always exist, but they're not necessarily justified by the incentives of the sellers if each seller is a monopoly over its own good. So there's a difference between market equilibrium and the issue of how the sellers will react in terms of their incentives. I guess I can take a couple of extra minutes.
Yeah, 2 minutes.
Okay, sure. So here is a more complicated view. We want to think of sellers. So in the best response case, each seller has a belief that the other sellers are not going to change their prices. And we want to think about sellers that have more complicated beliefs about what will happen in the next step. So here is a more general form of making beliefs. Each seller J will form beliefs about all the other sellers. And these will be labeled by levels. So the level 0, a level 0 belief is exactly what we discussed before. It's just a belief that the other sellers are not going to change their prices, or that the other seller S is not going to change its price. A level 1 belief is, it's either a level 0 belief or a belief that seller S will best respond to level 0 beliefs of the other agents. And in general, a level K belief is that for seller S is that seller S will best respond to level less than K beliefs about the other about all the other sellers. So the dynamic that we now want to consider is that we want to think about each seller best responding to some level K belief about every other seller. And we want to see where that leads us. So this is our main theorem. It says the following. It says, in fact, something more general than what I just described. It tells us that if we have any price update, and this price update satisfies these 4 very simple properties that I'll skip the definition because of lack of time. So if it's monotone, strictly subhomogeneous, and bounded, actually, I guess it's just 3 properties, but we need the 4th property for convergence. Then it is a strict contraction under some metric on prices, which is this Thompson metric that's defined here. Now, I'll skip the actual definitions, but what's important is the consequence. So one of the consequences is that if we have a dynamic where in each step we're applying such a price update, they don't have to be the same price updates, but in each step we're applying such a price update, which is monotone, strictly subhomogeneous, and bounded, then this system converges to equilibrium very quickly. So it's a linear convergence to equilibrium, which means that we're exponentially fast converging to the equilibrium. And this is true under the Thompson metric and also under L infinity or L2 metrics.
Sorry, does this have anything to do with the levels? I mean,
let me, this will be the next step. So now we consider a dynamic where in each step, every seller is responding to some level K beliefs about all the other agents. And these could be different beliefs in each step, and they could be inconsistent. So we're not having, we don't require any consistency of these beliefs.
So K, the number of levels forward can change from step to step?
The number of levels forward can change from step to step. The beliefs themselves can change from step to step, and they can be inconsistent among sellers in the same step or same seller in different steps. They don't have to have the same beliefs in each step. Then for a market which has this elastic and bounded demand, these updates are all monotone, strictly subhomogeneous, bounded, and stable, and therefore they converge to an equilibrium always. So this is basically the end of the talk. What I showed you also applies to asynchronous updates, where T now will measure instead of step, it will measure epochs, where an epoch is a period of time where there's at least one update to each price. The worst case, in fact, is best response. So if you have more elaborate beliefs, this converges faster. Here are 2 questions. So first of all, can we show something in the more general setting, games or some certain interesting types of games? And I think what's perhaps even more interesting is we allow here completely arbitrary beliefs that are not updated according to any information that is being revealed during this process. So in fact, we don't learn anything. The only thing we learn is what are the new prices. Of course, that's information. So it would be interesting to study or to come up with a plausible model of updating beliefs based on information that is being revealed through this process of the market. And to make it more realistically, we will probably need to assume that the information is noisy so that we don't know exactly the accuracy of the signal. But we know it contains some amount of information.
So the utility functions are not updated.
Utility functions here are not updated. This is a static situation. Because the convergence is very quick, you would assume that if the market changes at a much slower rate than the convergence rate, then it would appear to be close to equilibrium almost all the time.
I guess we'll thank the speaker and proceed with a few more questions.
Yeah.
So can you turn this around in a way and look to see, to try to infer something about the beliefs without knowing it a priori, given the way the market is going?
Yeah, I'm not sure I understand what you mean by that.
Let's say you're just monitoring the prices. Okay?
Yeah, okay.
And you developed all this and you keys or arbitrary and stuff like that. Is it possible to infer what the beliefs are?
Oh, I see. I see. Given a specific sequence of updates, can I try to infer?
I'm thinking about things like collusion and things like that between sellers.
Yeah. Okay. So we're actually assuming here that each seller, there are no coalitions. So they're not trying to.
No.
Yeah.
So that's what I'm saying.
Yeah.
Is there something that you infer in the belief that then you could apply this to a game or market where that you can then make a statement about, oh, well, this is not behaving?
Well, I guess I'm not sure about how to do it algorithmically, but obviously if you're assuming that each seller is best responding to some belief and they're changing the price in a certain way, you can definitely try to enumerate over all the beliefs that they might form and find something that is consistent with the change. There might be more than one solution, for instance. So
I guess I like the question. I think it's more like, well, you look at what's happening and then sort of look back and how sophisticated are the sellers in this game, right? How deep is their belief systems?
So you might try to infer this. I'm not sure. First of all, it's not clear that there's one answer.
No. That's fine. But
And right now, other than complete enumeration, I can't immediately think of a better algorithm. But you know, it's a good question.
Maybe you have one game that's played. You don't know it's played with K belief or K plus one belief. Can you tell the difference by looking at the outcome?
So it's a good question. We don't know the answer right now.
Work by Kevin Layton Brown, where apparently there's like these experiments where people play like very small games, and he tried comparing Nash equilibrium to scale level. I don't know the results. I know he's done something on that. It basically said these models fit much better to the data, but this is a richer model. You're learning many more parameters compared to Nash equilibrium. It's just
Well, Nash equilibria in repeated games are somewhat problematic, right? Because you have these grim trigger strategies that can force any outcome basically to your desire.
So he looked at very simple games.
Yeah.
Some experimental outcomes from like people playing like very small alternative games or something like that.
So there seems to be very extensive experimental evidence that, at least in settings that were tested in the lab, this is the way people play games.
So actually I have a related, it reminds me of this fantasy games that people are playing where there's some players who are much more sophisticated than others and are winning all the money. Is there anything in your theory that says like if someone has a much deeper belief system than the other guys, that they actually do much better in terms of extracting value from the system?
In our setting, no, because the whole thing, no matter what the beliefs are, no matter what levels each of the players has, no matter how deep they look into, it converges very quickly to equilibrium. So even just for best response, if everybody's best responding and one player is doing a very deep look ahead, then they might gain over this transient, but it's a very short period of time.
So the equilibrium is independent of how
Yeah, the equilibrium is independent of that because it's unique. So you're converging always to the same point. But in more general games, maybe that's a good question.
Is it even clear that there's a monotonicity? For example, if I think that you're thinking 10 levels deep, but you're only thinking 5 levels deep, should I do better for thinking that you're thinking more? I mean,
well, the only answer that I have right now is that best response is the worst case. Yeah. So we don't know that 5 levels are. What is maybe something that I can say about this? In this model, basically every player assumes that they're slightly smarter than everybody else. Yes, yes. So I don't know. It's definitely a natural assumption for many people.
And it's the absolute worst assumption to make when you go play poker with strangers. So.
Yeah. But this is the model that we have, that each player thinks they're slightly smarter than everybody else because they're playing at least one step extra.
Is there any way to reverse that? Yeah. Say, I think I'm slightly stupider than everybody else?
So you have a belief that everybody else is going to do something, but you're not going to best respond to that. You're actually going to, yeah. I don't know how to translate that into a strategy.
I think remaining questions of
Yeah.
time.
Okay.
Thank